All right, so we're on our last standing waves video. We now have to take a look at standing waves in a tube with one open and one closed end as opposed to two open ends. If you think about it, this is kind of similar to what everyone has done before with a water bottle when you blow air across the top of it. As a matter of fact, we'll do some demonstrations of that in class, and we'll do some other demonstrations of that are related to that. So this one you've all actually seen before. We're going to start it out pretty much the same way. We're going to derive the equation for this. This is our length L. We're going to have one open end and one closed end. So I'm going to denote the closed end by coloring in this end. And then the open end is going to stay, well, open. Now let's think about what open and closed mean. We said last time that the open end must be where an antinode is because the air particles, the air molecules are free to move around the open end. A closed end, that's not true. The air particles can't go through the closed end. So instead of that being an antinode, the closed end seems like it should be a fixed boundary, so that's where a node goes. Okay, so we need a node on this end and an antinode on this end. Now think about what section of a standing wave would give us a length that consists of a node at one end and an antinode at another end. Just to kind of refresh everyone's memory, remember standing waves look something like this, or at least they oscillate between these two kind of positions. What is the and so, well, actually, let's take a step back. When we needed two antinodes, when we had two open ends, what we did was the first antinode was, or the first set of standing waves looked like this, where right between my fingers, I don't know if you can see, you had two antinodes. That's the picture that you see in the first one. The second one, we just moved over one. We added essentially one more antinode, and now we have a full wavelength, and so on and so forth. Now, if we need to start with one, if we need to have a node here and an antinode here, what's the simplest way to do that? What's the least complex way to do that? Well, here's a node, and the first antinode would be right there. How much of a wavelength is it from here to here? That would be 1/4 of a wavelength, because this whole thing is a wavelength. So here would be half, here would be 1/4 of the wavelength. So our antinode, or our pattern, would look something like this. And we would write down that the length of the tube in this case compared to the wavelength is simply the wavelength divided by 4. Okay, so right off the bat we're starting off a little bit different. Obviously there are other types of standing waves, other modes of oscillation that we can have, so let's draw a few more. There we go. If we need to have a node at the left end and an antinode at the right end, another way we could do that is to use 3/4 of a wavelength. So that would look something like this. There's 3/4 of a wavelength. And we will write down that L equals 3 lambda over 4. Interesting. I'm going to put a 1 up here. Let's see if there's any patterns that emerge. The next way to fit in a node and an antinode in here would be here. That would be, looks like more than one wavelength. Looks like actually a wavelength and 1 extra quarter. So that would look something like this. Oh, I'm not going to draw this one very good, I can tell already. There we go. There's 1/4 wavelengths, or if we're writing it as a fraction, 5 lambda over 4. Now, this pattern is a lot trickier to see. Okay, this pattern is a lot trickier to see. the best way that I have been told to look for it is that you can see that this is it's the odd it's the odd multiples of a quarter of a wavelength that end up working, that fit the boundary conditions here. If you want something just like before, we said n was, for this was the number of nodes, for the waves on the string was the number of antinodes. Here n is equal to the number of nodes plus the number of antinodes minus 1. Okay? Or I guess you could also think of it being, no, that's probably the easiest way to think of it. And if what you notice, if we were to keep going, you would notice that these are always going to be odd numbers. So notice n cannot be even here. The reason n can't be even is because that would mean that we're dealing with some sort of multiple of a half wavelength. And half wavelengths would always go from antinodes to antinodes or nodes to nodes. That's not what we have here. We have node to antinode. And node to antinode is some sort of, it's in a denomination of 1/4 of a wavelength, because a node is 1/4 of a wavelength away from an antinode. And from the next antinode, you add a half wavelength onto that, but it's still going to be in terms of some odd number of quarter wavelengths. It has to be odd. So we see that L is equal to n lambda over 4, where n is an odd number. Again, we'll rewrite that in terms of lambda, and we get that lambda is equal to 4L over n. So in other words, in order to have resonance, to have a standing wave get set up in this type of tube, the wavelength of the sound wave has to be equal to 4 times the length of the tube divided by some odd integer n. Once again, we put that into our V equals F lambda equation. So the frequency is equal to V over lambda. So the frequency is equal to V over 4L over n. We end up with the frequency being equal to NV over 4L for n of 1, 3, 5, 7, ... One thing that's interesting to notice here is if you have two tubes that are the same length and the air inside them is at the same temperature, so same speed in air, and they're both at the fundamental frequency, this one will always be lower than this one. And one of the other interesting things is if you have these two tubes and you're trying out different frequencies in them, they will actually alternate as in terms of which one will resonate. First this will resonate, then you'll have this one resonate, and then this, and then this, and then this, and then this, and so on and so forth, until you get a set of all of these different tones. And they should all be evenly spaced apart, which is kind of neat. Perhaps we can do some sort of neat little experiment with that somehow. In any case, that's the end of our standing wave notes. Again, I really enjoy this derivation. This is the first time I've actually videotaped myself going over this. I really enjoy doing this derivation because I think it's a really interesting result, and there's some really cool problems that you can solve in situations and demonstrations you can do if you understand how standing waves in tubes and on strings work. We're going to see a lot more of that, this sort of stuff in class. And if you have any questions, please don't hesitate to ask. Next time you see me for videos, we'll actually be moving completely away from any sort of mechanics or waves for a little bit, and we're going to be looking at electrostatics. All right, I'll talk to you later.